Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today we will simply continue what we started yesterday. I was amazed by all the questions that you asked in advance. Very good questions. That's exactly the engineering's thinking. You know, the engineers who built these systems worked on all of these questions. So I left you with this. Yesterday, this was what's inside the name node. So you remember the name node is a process that runs on a machine that is at the center of the attention, and all of the other machines have data node processes. You can see them at the bottom there. And so we saw that there are three things in the name node's memory. We have the entire file namespace, the hierarchy of directories and files with access controls, users, groups, authorizations. Then we have a mapping from each file to a list, an ordered list of block IDs. And then we have a mapping from each block ID to each IP address or each host corresponding to a data node that has a replica of that block, right? So typically it's going to be three IP addresses, three data node locations, all right? Who is with me on that? Everybody? Awesome. And so now we are moving to the data node. What's on a data node? Well, you're going to be disappointed because, well, on a data node, there are blocks, and that's pretty much what there is in there. Now you know, because of the order of magnitude of 128 megabytes per block and let's say a terabyte drive in there, typically you're going to have a few thousands of blocks on the machine. And now, if some of you actually ever do this, if you can trigger the creation of HDFS clusters on Amazon, on Azure, it's just with a few clicks that you can do this. If you log yourself into one of the data nodes, and you do have the IP addresses and so on, if you open the firewall with port 22, you can use SSH to go to the machine, and then you're inside the machine on the local file system of the machine, not HDFS, the local file system, the local drive. And if you look on that drive, you will find a few thousand files that correspond to the blocks. So the HDFS blocks are physical files stored on the local drives of the machines, right? They are actually files locally. And these files, of course, are stored physically on the drive as 4 kilobyte blocks like on any drive, but from the perspective of HDFS, we don't care about this. This is a physical detail, right? This is really on the hardware itself on the machines that you would see this. So these are the blocks, a few thousands per data node, and every one of these blocks has an identifier here that is a 64-bit integer long that typically ranges between 0 and 16 quintillions, I think, which is probably going to be enough for quite some time. Even though some people said the same about 32 bits, and well, it wasn't forever either. But 64 bits, every block ID. What's more, the data node process also monitors the drive, checks that everything is correct, everything, let me explain correct later, that everything is okay, the drive is connected, it is in a good, healthy state. And it can also check once in a while the hash of the files, right, with an MD5 hash, so it can check that the block is also not corrupt, right? And if a block replica is ever corrupt, there are 3 of them by default, so if the other 2 are fine, you can still copy over the other 2 to replace the corrupt one, right? So you can recover from these things because of replication, okay? So right, so this is the local machine that detects any disk failures. Here I put multiple disks. You could also have multiple disks on the same machine, right? That's entirely possible too. Like you can have also on your laptop and desktop computer at home. Okay. A small hint, and also an explanation of what it means for random access. It is also possible, and you know, because it's a file on the physical drive, to read a block partially. So it's entirely possible for somebody to connect to the data node and do not ask for the entire block of 128 megabytes, but a byte range within it, right? A selected byte range. This will be especially useful in a few weeks when we use MapReduce, because there are occasions where we don't want to read an entire block. We just want to read parts of it. Then you might think, okay, but then we have random access, right? Because we could technically read anything anywhere, and you might even, so yeah, you can think this is real time. But it doesn't work like this, because don't forget about the latency. The latency when you are on a network, on HDFS, whenever you type a command to do something, is going to be 1 or 2 seconds. So it has nothing to do with the latency you have in a local file system, so you are nowhere near efficient random access to the files in spite of this, right? So this is used with, what is the name for that? I forgot the name. With care, with moderation, right? We don't do that all the time. There is something else with parsimony. I was looking for the word. Another thing that I would like to clarify, because it was asked yesterday at the end of the lecture, is what if a block has less than 128 megabytes? For example, a file, an HDFS file that you want to store. Let's say it's only 10 megabytes. Well, in that case, there is no waste of space, because if you have a file of 10 megabytes, it will be one block of 10 megabytes, and that's not going to waste the remaining 118 megabytes, right? So it's only going to use the 10 megabytes that it actually takes. And in fact, it happens always for the last block of any file, right? When you have a file, each block is exactly 128 megabytes, and the last one is going to be less, and there is no waste of space for the remainder. For whom is that clear? Right, very good. Okay, so this is a difference with the local file system, because on your laptop, there is a waste of space. The blocks are really 4 kilobytes, and it takes the whole 4 kilobytes. So that's the difference. Okay. So now that we know what there is on the name node and we know what there is on the data node, we'll see how they communicate with each other, how the whole thing works. And so there are 3 characters in this piece. So we have the name node, we have the data nodes, and we have the client. So let's do it one by one, right? We'll first see the client with the data nodes, and then we'll see the name node with the data nodes, and then we'll see the client with the data node. So 3 different protocols. So let's, oh, that's just the same slide, but I put more information in there, but I'll go in detail about that. So I'll start with the client protocol, then the data transfer protocol, and then the replication pipeline. So the client protocol is when a client wants to do something with HDFS. Well, the default answer is you connect to the name node. That's your first point of contact. It's the name node. Technically speaking, it's an RPC, a remote procedure call connection, right? So it's like you have a language, and it feels like you're talking to a local program, but in fact, it's all sent over the network and back, right? So remote procedure call. And so the client might contact the name node to create a directory, or to delete a directory, or to signal an intent to read a file, or to write a file, or to delete a file, or to change user access rights, and so on. So these are metadata operations. And in the cases that the clients want to read or write to some files, then the name node is going to reply with data node locations, with block IDs, and everything the client needs to know to access the data. So far, so good? Yeah, so that's the metadata. There is no data in there, just metadata and communication to signal intent to do something and synchronize on the high level. Okay. Next, the data node protocol. So the data node protocol is between the name nodes and the data nodes. The first thing to know here is that it's always the data node that connects to the name node, never the other way around. The name node is never going to connect to the data node. You know the client-server thing, right? A client connects to a server. And here, if you think of client-server, and I don't mean the HDFS client, I just mean the client-server architecture, the data node acts as a client of the name node. So what does it do, the data node, when it connects to the name node? Well, it does several things. The first thing that it's going to do is it registers. When a new data node joins the network, it registers with the name node and say, hey, I'm here, I'm new, and I'm available to store blocks. This, of course, is done with secure authentication, like Kerberos, this kind of thing. So it has to prove that it is legitimate to join. So it registers. Once it has registered to the name node and it's in there, then every 3 seconds, you can change that, of course, in the configuration. Also, they change the default value once in a while. But every couple of seconds, the data node contacts the name node and says, I'm here. I'm still here. I'm still here. You know, like a heartbeat every couple of seconds just to say, I'm still here. So that way, the name node will know if one of the data nodes has a problem or crashed. It will know within a couple of seconds. The second thing that the data node is doing is that every couple of hours, typically 6 hours, it used to be 24, the default. And again, you can change it if you're not happy with this, but now I think it's 6 hours. The data node is going to send a full report of all the blocks it has to the name node. Like this is the thousands of blocks I have. These are their block IDs, their hashes, and so on and so on. So whole block report sent to the name node, and maybe some health information about the disk and so on. So this is the third thing that it does. And also, a data node can send to the name node some communication that says, I received the block. That's another thing that it can do. Then, every time the data node connects to the name node might say, by the way, since you're connecting to me, please do this and that. That's the block operation. So for example, it could tell the data node, oh, this block here is under-replicated because it only has 2 copies at other places. Please make a 3rd copy on your machine. That's the sort of things that the name node might tell the data node. So it can give instructions to the data node to do this. So again, I insist, it's always the data node that initiates the connection. And when the name node gives instruction to the data node, it's always in the response to the initiation of the connection. Who is with me? Yes, we have a raised hand over here. I'm not sure we have extra microphones in there, so we'll just repeat what you say. So go ahead. Oh, so there are configuration files on every machine that are actually XML files that specify who is the name node and what is its address and so on. So there are configuration files. Remember that these servers here are all within the control of the company, or there is a sysadmin, right, who administers the whole cluster. And so when you do that, you have to pay attention to have exactly the same configuration files on every machine. Right? If you have different configuration files, then it's going to not work. There's going to be issues. So this is one of the first things that the sysadmins learn when they use HDFS. They really have to have exactly the same configuration. And this is how the data node know to which name nodes to connect. Oh, no, there is a network connection, right? So when the data node connects to the name node, it knows that it's connected to a machine, and it knows because of the configuration and other means that it's legitimate, right? That's how it works. So the name node knows that the data node is legitimate because of Kerberos. There is an authentication in place. So the name node is sure that whoever connects is legitimate. And the data node who connects to the name node, they know it's legitimate because they know from the configuration who that is, right? Does it make sense? Yeah. All right. Any other questions? Yes, I see a few raised hands. Go ahead. So the data node doesn't know which file owns which block. All the data node knows is it has blocks, and each block has a block ID. So the block report basically lists all the blocks, like these are the block IDs that I have, for which I have a copy, and with some hash, some MD5 checksum, so that the name node can also check that it's not corrupt across machine. Just the block IDs, yeah. It cannot send the blocks themselves because that would be just insane. And there is no, the data node really is blind with the files. It has no idea what the file namespace is. It just has block IDs and the content, right? Yes?
Does the name node already know all these things? Like the block report?
Yes, if things are going well. But when things are not going well, then the name node might forget. And an example of that, and that's why I will answer the question that was asked yesterday, if the name node crashes, then it's lost. So then we don't know. And so the block reports enable a recovery of this information. So then it's rebuilt from the block reports when you lose the mappings. And also, the block reports might inform you about a corrupt block, right? Because maybe everything is normal, and then at one point there is a block report that arrives, and then an MD5 checksum changed, and then the name node sees that, okay, something's wrong. Then it's going to instruct the data node to re-download a new replica. Does it make sense? Yeah? Yes?
Name node, also the name node stores the hashes of each block and so on, so that we can verify, okay, this one was.
So the name node about MD5, you mean? Yeah, the name node, since it receives all the reports, it can see if the MD5s are different. It will notice if different data nodes have a different checksum for the same block, then it knows something's wrong. Then it's a majority, it's a quorum, right? You basically see, okay, 2 out of 3 are the same, so it's the third one that is likely to be corrupt. Yes, it's a good idea to have an odd number. Odd numbers are good. They will also be back the odd numbers with the name node failures. Yeah. Okay. It's the same in real life. When you have a team or a committee, you should have an odd number, because if you are in disagreement, then at least it's not cut in half, right? You don't have a tie. Any other questions? All right. On Zoom, also not? All right, so I'll continue. And if you're interested, I can also investigate more on what the whole thing in the block report. I could look at, give you more details on that. The third protocol is between the clients and the data nodes. This is where the block data actually goes, because whenever the client reads or writes, the data goes between the client and the data node. More exactly, there is what we call a pipeline, a replication pipeline. So whenever the client is writing some new data, it's not going to connect to 3 data nodes. It's going to connect to one of them. And then that data node will forward to another data node, which will forward to another data node. So it all occurs in a pipeline fashion, right? And when you read, of course, you only read from one place, not from everywhere. For whom is that clear? Right? So this is actually pretty simple, the pipeline. Okay, so again, the metadata, I told you, you can create a directory, delete a directory, write a file, append to a file that I didn't say, read a file, delete a file, and so on. So that's, you have to connect to the name nodes. So now I have an animation for you to show everything that gets into place. And I try to refine it every year, because there's always good questions that go even further down in depth. So it's a good time to do that. So let me take the example of a client that wants to read a file that's already on HDFS somehow. Where does the client connect? You can say it directly. Name node, exactly. You all agree with that. Always the name node first. What actually happens is that locally on the client, it's a Java program that is running. There is a Java API, and you might know in Java about input streams, output streams. Whoever heard of that? Right? So this is an API. And so actually there is an input stream that the client opens, that the programmer opens, and it's in the implementation of the input stream that all of that happens. So it's the implementation of the input stream that's going to take care of talking with the name node and data nodes and so on. So this is why I put input stream in there, just so you know that this is the Java code that does that. So it's asking for a file saying, hey, yes, there is a, yes, go ahead.
That's whether the replication is done asynchronously or not.
It is done synchronously up to a certain number, and then asynchronously after that number, all the way to 3. I will actually show it also on the animation, so you will see. So it starts synchronously and finishes asynchronously, right? Actually, exactly like in Dynamo, right? In Dynamo, you are synchronous all the way to W, and then it's asynchronous all the way to N because you don't wait after W, right? Okay. Just in a few seconds, probably you will see the animation. So we ask for a file saying, hey, I would like to read that file. It has this path and so on. So the name node is going to check that the user has access and so on. And then it's going to say, okay, the file exists. There is no problem with that. Here are the block IDs of that file. And here are the data nodes that hold the copy of each one of these blocks. Plus, I was so kind as to sort it for you by distance from you and to the data nodes, right? So I'm going to put the first one the closest to you, and then further apart, right? So it's nicely sorted by distance to the client. So far, so good. So now the client knows the block IDs and it knows where to find them. I'm going to assume now a sequential read, right? We see with MapReduce that we can also do things in parallel, but right now it's sequential. So it's through the input stream. So the client is now going to connect to the data node, block ID, black block ID in the order. It starts with the first, reads the bits, and then connect to the second one, reads the bits. And the user of the input stream will not even see the boundaries between the blocks. They will just see the incoming bits, right? Yes? Because the name node is aware of the topology of the name nodes, the data nodes, sorry, because it's in a data center. I will also have slides. You have such good questions. I also have slides about this. So the machines, they are on racks or piled up on racks, and then there's many racks, and then they are in a room, right? And so machines that are on the same rack are going to be closer, and on different racks, they are a bit further away, right? So you can compute with the network topology and the network cable. And the name node is aware of this, right? It knows exactly how it's connected where. Then you might be wondering, but wait, the client might be outside of the data center, right? So what does it mean for the clients to be close or not close to a data node, right? But we will see, and again, when we see MapReduce and Spark, that very often the client is also in the data center. So the client machine is also in the data center. And typically what people do when they want to use a client to access HDFS, they first SSH themselves into a machine in the data center, and then in the data center they access HDFS, right? So this is why it makes sense to talk about the distance, right? But again, the short answer is the name node is aware of the topology of the network between the machines, right? Does it answer your question? Yeah, all right, other questions? Okay, then I continue. So that's for reading. And now what if we write? So if we write a file, it's now an output stream, which provides an abstraction for writing bits. So, well, I showed you where does it connect to? Of course, the data node, the name node, always the name node. So the client connects to the name node and signals its intent to create a new file with a specific path and name and so on. So the name node is going to check the user, the credentials, and so on. And it's going to say, okay, fine, I'm going to create that file for you in the namespace. And here is the first block ID that you can use. And here is a list of data nodes that should receive replicas of that first block, 3 of them by default. So now the client now knows the first block ID and the first 3 data nodes. So the client is going to organize a pipeline. It's going to connect to the first data node, the closest one. We follow the topology. Again, you connect to the closest one, the first one in the list. And then it's part of the protocol. The first data node will organize a connection with the second one, which will organize a connection with the third one. So it's all pipelined through. And once this is done, the client starts sending data. So the actual bits of the block, right? How many bits for a block? How many bytes? 128 megabytes, right? By default. Of course, you could change that. You can make it 4 gigabytes if you're a big fan of 4 gigabyte blocks. All right, so we send the data over. Now, let's dive a little bit more into the details, because what is going on here, it's over network cables with a network protocol, right? And the way a network protocol works is you don't just send a 128 megabyte network packet, right? That's not how a network works. But when you have a network, you actually send small packets, like 64 kilobytes packets. That's more like what happens in a network protocol. But I insist that this is only what happens over the network when you upload the block. And once it's there, you forgot about these packets. This is only a network thing of what's going on the network cable. So basically, you have all of these. Yes, there is a question on Zoom.
Is the data simultaneously written on all 3 data nodes?
It's pipelined through. So basically, oh, you mean read, not written. It's about reading?
It says written.
Writing or reading?
It says written.
Oh, written. So it's exactly what is in here. So basically, when it's written, want to make sure that I'm on the right slide. When it's written, the bits flow over this network cable right here to that machine, and then it flows to that machine, and then it flows to that machine, right? And then the question was simultaneous. So is it like you have the entire 128 megabytes here, and after that you have the entire 128 megabytes, and after that you have the entire 128 megabytes? No, because of this, because you have these 64 kilobyte network packets. So it means that once the first machine has received a few packets, they can already forward them to the next machine, right? So this is why it's called a pipeline. You really, the data flows through all the way to the 3 machines in that way, and you don't wait for the entire block to be transmitted before you start transmitting to the next machine. Does it answer your question? Yep. Was there another one?
Can the user safely disconnect after the data reach the first data node?
I'll tell you about that. That's exactly this, the hack right here. So what happens is that then this machine right here, the client, so the Java implementation of HDFS, keeps a list of the network packets that are in there. It keeps a list of them with a check. And so whenever it receives an hack from through the network, so there is all the hacks flow the other way around and all the way back to the client. And then the clients can check. It says, okay, this one I have an hack, this one I have an hack, this one I have an hack, not necessarily in the right order, right? But the clients can only consider that it's done after it has received a certain number of hacks for every one of the network packets. By default, 1. That's called the minimum replication factor. So after the client has received at least 1 hack for every one of the network packets, then that's safe. It's done the minimal replication, and then it can consider that the block is transmitted, and then it continues in the background to transmit to the other nodes. Does that make sense? Yep. All right. Okay. So again, we have an hack. I can't remember if it's called an hack queue or an hack. There is a name. There's basically a data structure that just keeps track of how many hacks you've received for every network packet. Once there is an hack for at least 1 for every network packet, then the client considers that that block is written and will connect to the name node for the second block, right? And then the second block ID arrives, the new data nodes for the first block arrive, and then it's going to again organize a pipeline, send the data over, all pipelining through in network packet of 64 kilobytes, and then you receive the hacks. And when you have at least 1 hack for every network packet, then you consider that you have reached this part. So this is your question about synchronous, asynchronous. So it's synchronous until you have at least 1 hack for every network packet, and then continues asynchronously all the way to 3, right? Okay, that can be changed, by the way, all of these parameters, 1 and 3. Okay, and then that goes on and on and on and on and on for the blocks. And then the client, when it has determined that everything is fine and it received all the hacks that it needed and so on, it can inform the name node that it's done, writing all the blocks, and tells the name node, now you can release the lock and allow other people to read that data and close the file. Yeah?
Is the hack sent by the last node on the pipeline?
The hack is sent by every node, but always respecting the pipeline. There is no direct connection to the client from these ones, right? So these ones, it really goes like this all the way back to the clients, right?
Does the client might tell the name node how much data it intends to send beforehand?
Oh, that's actually a good question. I don't know if it does, because technically it could just go on and on and on and on, sending blocks. And I would think that it's best to have the flexibility to not know in advance, because when you imagine your map reduce and you're producing data, you might not know in advance how much data there is. So then my guess answer would be that you don't know in advance and you don't tell in advance how much data there is, right? And then I'll come to you. Yeah.
Case, what would if, for example, data node 1 and data node 2 can't communicate anymore? Would the write fail?
Oh, yes, absolutely, that can happen. And then you are in the situation that you would have only one hack. For example, if it's disconnected further down the pipeline, but it works with the first data node, then this is fine, right? Then you have this minimal replication factor. And what's going to happen is that later, after the file is written, the name node will notice from the reports that the blocks are under-replicated because there's not 3 copies, and then the name node will instruct to the data nodes to make a second and a third copies, right? So that can be recovered later, as long as you have your minimum replication synchronously checked, right? Was that the question? Yeah, awesome. And then if it's the first data node that fails, then of course you're blocked, right? Then you have a problem and you have to try again. Yeah. All right, yes, go ahead.
That it's done, then it's released the lock so other people can read. So the versioning of the data in the HDFS is linear.
It is linear, yeah. It's strongly consistent, yeah, which causes a problem for availability, but we'll talk about that. Yeah, so yes, it's strongly consistent. There is a lock, and you cannot have any deviation or branching that you don't have in HDFS. Yep. Yes. So the question is about the lock on the name node. So the lock is on the file. So this is for strong consistency. While you are writing a file, you don't want other people to already try reading that file. So when you write, you're very cautious and you put a lock on that. That forces people to wait until the file is fully written. And then when you release the lock, then people then can start reading the file, other clients. Right? Does that make sense? So you're asking if multiple clients can speak to the same data node at the same time? Yes, that is possible. Yeah, absolutely. Because if you're writing different files, you're also writing different physical files on the disk, so it's entirely possible. Yeah, it's even a feature of HDFS, right? That you can connect in parallel and interact with it in parallel, right? Does it answer your question? Yeah, awesome. Any other questions? Yeah, over here. I wasn't hearing very clearly. Maybe I should get closer. Go ahead.
That the user will send a notification to the name node to
Yep.
release the files.
Yep.
If the user does not send it, then this file will be blocked for everyone, right?
Yes, absolutely. The file is basically not finished being written. That is correct. So you do rely on the fact that the client is going to correctly communicate to the name node.
Say that the user send a message to the name node to write all the code base, then all the code base is blocked for everyone.
Yes, absolutely. But the case where a single client is writing the entire code base does not really happen, right? In practice, you really have hundreds of clients that connect to HDFS and write all the files, right? Yeah. But you're correct. Like as long as you're not done writing a file, then that file is not accessible to anybody else. All right. Then I think there are cases in subsequent releases that they lighten a little bit the lock, saying, you know, it's kind of okay for other people to start reading for the blocks that are already in there. But I think they were cautious about it because you don't want to make a mess out of it. Yeah, go ahead.
What would happen if a data node fills up? Does it fall back to the name node?
If a data node becomes full, the disk is full. Yeah. So it's again the same idea that we had, you remember, in the storage stems for Azure Data Lake. You basically maintain a maximum, you fill the disk all the way to 80%, 90%, like you have some sort of maximal load capacity. And then what happens is that the name node is going to instruct moving blocks around, moving replicas around. So if a disk becomes too full, then the name node is going to move the blocks over to other data nodes, right? Does it answer the question? Yeah. Right, I don't see any more raised hands, so not on Zoom. All right, so then we release the lock and we are done. And there's a final hack. That's the file is written. And just in case, because again, we only checked for one hack for every network packet, just in case something was wrong and the replication all the way to 3 didn't work asynchronously, no big deal, that can be taken care of later. Because of the block reports, the name node will notice that a block is under-replicated, and then it's going to instruct to further asynchronously replicate. Everybody's with me? Right, okay. Okay, still have a few minutes to tell you a few more things. So, yes, go ahead. The block reports, right? Yeah, they're generated by the data nodes.
Oh, I don't have data in this node because X, Y, and Z. So the communication is interrupted in order to report to the data.
So the question is whether the data node connect to each other. No, they don't. They just connect to the name node. So the data node just sends a list of the block IDs and MD5 checksums and so on. And it's the name node that checks that it's the same across machines. Maybe I should amend my answer because that's a contradiction. They do connect with each other for the purpose of transmitting data, right? So if the name node asks a data node to download a block replica from another data node, then of course they will connect to each other, just like in the replication pipeline, right? But they will only connect to each other for that, for sending data over, right? Does it answer your question? Yeah. Awesome. Yes?
We said that data nodes only name node to these pulses, but do they bypass this to connect with the client for the acts? Like we said, the data nodes send the acts to the
Yes, absolutely. So for the acts, it goes through the pipeline. So yes, in that case, this data node here is going to send an ACK over to the client, right?
bypasses the name.
Yes, that bypasses the name node. Here, this is a protocol just between the client and the data nodes, and the name node is not involved, right? It's what I showed earlier. Here, that's basically the 3 protocols. There is a client protocol here, there is a data node protocol, and there is here the replication pipeline, right? It's always, that's how networks work. It's always 2 machines, a client and a server, whenever you have a connection, right? Okay. So now a few words about the network topology and the replicas. So by default, it's 3 replicas for every block. You can change that if you don't like it per file. You can make it 5, 7, an odd number is ideal. So you can increase that if you want. So now we need to decide where to place them, right? And for reliability, if we place them on the same rack, for example, and the rack crashes, then we have a problem. The read-write bandwidth is also important, that you have to make sure the network is not overloaded and well distributed over the cluster when you access it via MapReduce, you want things to be well balanced. So this is what I said a few minutes ago already with this topology of the network. The fact that the nodes, they are actually piled up on top of each other in racks like this right here. And then we have several racks. So you see the nodes can be close to each other or not close to each other. For example, A and B here have a distance of 2. It's just the number of edges going to the rack and then going to B, distance of 2. And here it's a distance of 4 because you have to go to the rack, then inter-rack communication, and then back to B, right? Do you agree that this is farther away, this is closer? And so here's the replica placement strategy by default. Replica number 1 is going to be put on the same machine as the client. This is then when you can be like, wait, what? The client, same machine as the data node, what's going on? But yes, this is absolutely the case that very often when we use MapReduce or Spark, the client of HDFS in fact runs on one of the data nodes, right? So this is why in that case, you just write it on the same client. Then that's great because it doesn't even go through the network. It just gets written to the disk locally, right? So that's super efficient with MapReduce and Spark. So that's replica number 1. And of course, if the client is outside the cluster, which is also possible, then it's picked randomly. Everybody is with me, right? So replica number 1. The second one, we put it in a different rack, just in case the first rack completely fails, a different rack that we call B. Replica number 3, also in rack B, but different nodes in rack B. Why the same rack? That's also for the efficiency of the writing pipeline, the replication pipeline, because then it keeps the distance reasonable. And I explained shortly why not 2 on the rack A and 1 on the rack B, right? I'll explain also that. And then for more replicas, if you have higher than 3, the replication factor, then of course at most 1 per node. It doesn't make sense to store the block twice, 2 replicas on the same node. And at most 2 replicas per rack, right? Doesn't make sense to go 3 or beyond. Now let me explain. So this is what happens. You have the client right here that is sitting on that machine, same as the data node. So it's going to create the first replica on the same machine, and then the second and third replica on a different rack, 2 different machines. So this is what happens with 2 blocks. If you write 2 blocks, then 2 copies of the replicas will be here, and then 2 replicas on another rack, and then 2 replicas of the other block, maybe on some other rack. It can be different every time. So you see here intuitively, it spreads things along the cluster, right? But if you did not do that, and if instead you said the first 2 replicas are on the same rack, do you see the concentration here? You start having a lot of replicas concentrated on that rack, and that's dangerous because that can fail, right? And also for MapReduce, for reading the data in parallel, it's not good to have too much concentration. We have a question?
Are all nodes in the same physical data center, or are they spread among many data centers around the world?
In HDFS, they would be in the same data center. So the name node and the data nodes are all in the same data center. This is why we have this 100,000 machine limit. But there are newer technologies that I'd say a few words about, like Colossus, that do involve thousands of data centers, all over the planet, right? So these are the newer generation systems. But this one is the same data center, right? Just checking the time that I don't go over in time. I'll do a cliffhanger. So the name node is a single point of failure, and one of you actually noticed that yesterday. What happens if the name node fails? Well, maybe you can do some backups, right, if it fails. So maybe we can back up the file namespace, we can back up the mapping to block IDs, we can back up the mapping from the block IDs to the IP addresses of the data nodes, right? But in fact, no. You only back up the file namespace and the mapping to the block IDs, 1 and 2. You do not back up 3. Why? That's the question you asked earlier. We do not back up the mapping to the data nodes because of what?
Blocks and ones.
Yes, the block reports. The data nodes will send their block reports later, and so you can reconstruct that. So it's 1 and 2 that we need to back up. So we back up them to a namespace file, and then when people continue to use the system, instead of modifying the namespace file, we just keep a journal. Oh, we created that file, we created that, but it's just a journal that has a sequence of updates and that grows over time as HDFS is being used, right? So that is going to grow over time as you add data. So then you can also do extra backups to be extra safe to S3, the Glacier version where it's super cheap. So you should copy that everywhere, because if you lose that information, you cannot rebuild the files. You have the blocks, but you don't know how to assemble them. And so tomorrow I'll tell you how we use that to reconstruct and how we can make it super fast. So thank you very much, everybody. And so you know tomorrow, next Tuesday. Enjoy your exercise session.